Okay, boundary value problems. Boundary value problems. So initial value problems were initial value, right? Boundary values are boundary values. Hooray, right? The whole point is that now the initial is technically a boundary. It's a boundary in, quote, time or not. The differentiator is that now we have boundaries at either side. So for a 1D problem with information at both sides, we could conceivably solve for that simultaneously, right? We couldn't really do that with a time stepper unless we're doing something like implicit methods. And in fact, that is the whole point behind implicit methods. But with initial value problems, we typically don't know anything about the other side. Yeah, or anything useful anyway, because we should eventually know that entropy, heat death of the universe. Which has come up because people have considered doing space-time discretizations, and they say like there is an ultimate end for which we have information, but never mind. By the way, interesting research project topic. So the shooting method. The whole point of the shooting method is to try and use whatever we did for IVPs, for initial value, for boundary value problems. And the nice thing is that we've already got all that machinery. Everything's already built. We've already done now the adaptive time stepping now comes in for, imagine that you want to do a boundary value. So you've got 1 and 2, right? If you were doing this with finite difference, you would have to set out your mesh, right? But with the shooting method, what you're doing is adaptive time stepping. So maybe you want to go like this, like this, like this, like this. Everything's handled automatically by adaptive time steppers such as, anybody? What's the go-to adaptive time stepper for initial value problems? RK45 for explicit, multi-step for implicit, right? So the concept is super simple. You choose which boundary you're going to consider to be your initial value. It is completely arbitrary, obviously. You solve it as if you were doing an IVP, and then you check whether or not the other boundary condition is met. You throw that into a root finder, and you're done. Great. Some of the benefits, it's very simple. So I tried to put down these pros and cons, and once we talk about finite element, I can try and bring it together into a big table, just for concise kind of summary. It's conceptually very simple to be able to do this. We already have a lot of these IVP solvers, which is great, and they're well tested, they're very accurate, they're reliable. It's good for linear problems, and apparently also mildly for nonlinear problems. I think it does struggle with the nonlinear problems because then we get into issues with numerical stability. That's when we need the implicit method, so on and so forth. Kind of a weird balance going on. Heat transport in here. Flexible for adjustments. Yeah, so again, like the whole point is that we can already do that adaptive time stepping, which is something that a lot of these other discretization methods kind of struggle with, to be honest. Yeah, and it's especially with low dimensional problems, but at this point, the computers are strong enough. It is pretty sensitive to the initial guesses because now we're doing a root finder, right? So if your initial guess is way off, you might not find the root. It might take you forever to find the root, right? We're playing this game again. If you do have oscillatory solutions, so for example, if you did have something that was a sine wave, right, it's going to struggle a little bit because it's going to constantly be readapting it every time. High dimensional, it has different problems because now what is an initial value, right? If you have a 1D domain, choose one. This is your initial one, that's your final one. If you have 2D, what is initial? Right? It's not really that one. It's not really that one. Maybe it's these two combined that go to something like that, and it gets really kind of wacky. But for certain boundary conditions, maybe that would work, but now we're into some kind of heuristic like that. Numerical root finding, well, guess what? Any implicit method has root finding anyway, and numerical stability. So one of the original motivating needs for numerical methods in the first place was killing other people, right? And by that, I mean ballistics, right? So you're in a ship, you're moving that way at that speed, your enemy is over there, you're doing that, you have wind resistance, where do you aim? What's your angle? What's your inclination? How much gunpowder do you load? All that's differential equations. Okay. So this one is, you'll notice that it's actually pretty familiar. We did this with finite difference already. Launching a rocket needs to have 50-meter altitude, 5 seconds, ignoring drag. What would the initial speed be? So first of all, it's a 1D problem of altitude as a function of time, y as a function of t, right? Given gravity, we know the equations of motion. Super simple. Here's a boundary condition, 0 and 50 on either side. Remember that we have to do reduction of order for this. Do you guys remember what reduction of order means? We covered it at the end of the last week. You got it. So the whole point here is that you take your altitude as a function of time. You need the second derivative. So you define an auxiliary variable, and then you use that as derivative with respect to time as your acceleration term. And off you go, which is nice because now you just have a set of unknowns. Let's see. So we need integrate. I didn't use BVP here. I used it later on. That's fine. Root, that's our model. So now our model has two inputs, y and v. And this is bad programming behavior on my part to say yv is equal to y. Ignoring that. Right, you've got your initial conditions, you've got your time span, which is your x domain effectively, your boundary conditions, and then what you have to do is you define a function that solves your initial value problem, right? So given your initial guess, you solve your initial value problem and you find what your altitude is at the end, and then you throw that into a root finder. So there's a little bit of defining functions that call other functions going on just because of the structuring of how the root finder is expecting to query your function. So like here, for example, I have, yeah, so this is lambda. Do you guys remember what a lambda function is? We didn't really talk about that too much. Lambda function is a really like kind of shorthand way. It has a lot of uses. It's used for procedural programming. But the whole point is that you want to be able to define a function really concisely and not even bother with a name. So lambda is called like an anonymous function. And the whole point is that you create a nameless function. It takes v naught and it evaluates this other function, which is shooting method, minus your boundary condition at the end. Right? So it's just a way to kind of conceptualize that and pass that function as an argument to something like a root finder. Just a nice little shorthand. Okay, and you give it your initial value. You solve for it, and yes, I accept. Run. It's nice to output the solution just because that does have a fair bit of information. You guys have probably all used at this point one of these methods, the root finder or the initial value or something like that. Do get into the habit of just quickly checking the success and the message. Usually, if it's short, you're fine, especially if you see the word converged. Success is nice because sometimes when you're doing these things, like you'll get some wacky answer and you'll be scratching your head for a couple hours, and then you'll see this and it says failed. Like, oh, okay, well, that was fine. Effectively, yes. Yes.
What is
function value? Yes, yeah. So success status, this is just a nice, like, as far as I know, the difference between success and status is basically Boolean. That being said, I mean, true is also Boolean. True and false is actually Boolean. So I think one might be like a bit more expansive. You could have different integers being that it succeeded, it didn't succeed because of this and this and this. Not actually sure. Function value is the function at that value. Which value? X. Method, hybrid. This is for the root finder. So the root finder is the, what is it? The line search coupled with the, I think the Levenberg-Marquand algorithm. That's how it's finding it. Number, this is number of function evaluations. So this is how many times it had to call that solve IVP method to be able to find it. And then some information about the Jacobian. Not sure what R and QTF are. And then this is just plotting the, printing out the data, right? So that's your initial one. That's the initial velocity. That's what we're looking for. And double checking, yes, it does actually reach 50 at the end. Looking at the analytical solution just for kicks, right? Because we can integrate this exactly. That's what we see the ballistic pathway is. Okay, any questions on shooting method? The application is frankly a bit limited, to be honest, because if you're going to be using something like a finite difference solver, like if you're going to be solving these sorts of equations, chances are you're going to want to use the general one. You're not going to want to like handcuff yourself to a 1D problem. Unless you really want to solve a 1D problem, to be frank, if you have a 1D problem, I would look for an analytical solution, because chances are there's one for that. And that analytical solution always trumps numerical solutions. Okay. Collocation algorithms is kind of neat. And you'll see neural networks there. That is not the context of using neural networks to solve PDEs. That is the modern standard, actually. The whole idea with this one is, so we're using our previous toolboxes and stuff, right? We have ways to interpolate functions. We did an entire week of that. Let's use those, right? So the idea is that we set a set of points that we're going to use for this function, kind of like we do with finite difference, but it doesn't have to be evenly spaced. That doesn't matter. We define an interpolation property, an interpolation method based on the function values at that point, or something else, right? The whole point is that we are using an interpolation based on those points, okay? But that has like weights. For example, RBFs has a set of weights. Cubic splines have a set of weights. You could do a single polynomial, but then you're into higher order polynomials. Don't use higher order polynomials. You want to use piecewise, which is piecewise cubic, i.e. splines. RBFs are a great one because you can go to n dimensions, etc., etc. You apply the ODE at each of your points, right? And calculate your residual. So now because you are interpolating, right? The whole point with this is if you were doing a function like that, why not? Those are my points, right? I can fit a polynomial. I could even fit a high order polynomial. Let's say I was bad. I actually did that. It's order, what's that, 7, right? And it looks something like that. Well, now I could apply my ODE to that. I could say, what is di y by di t minus f of y and t? And I could call that my residual, right? Now my residual is actually a function of whatever I'm using to fit y. So if y is a function of your weights, polynomial weights, RBFs, Fourier series, blah, 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 right? Fourier series is an example of this, by the way. Then I can do a root finder, or at the very least, at least squares, to solve this, which is kind of neat. Okay. Some of you can use basically any kind of interpolator function, or any function which gives you any interpolation method which gives you a result, right? That you can apply that ODE to, and then you minimize that residual. Okay. Obvious one, splines, we already talked about it, good for 1D or 2D. Radial basis functions, right? RBFs, if you recall, those are good because they go up to ND, which is good. And I have an example to show you guys. Neural networks, right? This is an interesting one. You know what? I'm gonna come back to that one. Spectral methods. So usually when people think about spectral, they think about Fourier spectrum. That is not the only way of doing spectral methods. It's a more general terminology that has to do with sets of functions that I don't think they even need to be orthogonal. They have a lot of benefits. You guys remember how Fourier series are orthogonal? So if you integrate, we just did the assignment, right? So if you integrate the function over the Fourier, then it doesn't coincide with the other ones, blah, 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 blah. There's a whole set of functions. Chebyshev polynomials, I think, what are the other ones? Legendre polynomials. I think there's Euler, like everybody has their own set of polynomials. Some have that orthogonality principle, some don't. Doesn't actually matter, because all you're doing is you're throwing this into an optimizer. Neural networks. So the idea within neural networks is you could do some kind of, like, the whole point is that you want to model something that looks like that. You could apply a neural network to each point. You could say that the neural network has some understanding of this discretization, and we'll give you a function like that, right? And then you have a bunch of weights in your neural network, and you say, okay, go optimize it, go find it. The current way of using neural networks for PDE solution doesn't even have that discretization. It just says, here's an equation, go find a solution, make sure it works according to the boundary values, and then I'm going to poke it. Right? So there are a lot of different ways to do that. So neural networks in the modern application aren't examples of co-location algorithms. They're kind of a new animal. It's kind of neat. Okay, pros and cons. They can handle complex geometries and irregular domains. Because you're doing an interpolation function, you don't need regular grid spacing. Do whatever you want, with the exception that you have to be able to satisfy whatever method you're using to make your interpolator. Right? So whatever, for example, RBFs struggle when you have points that are too close together. You start to get indefinite matrices, right? So your meshing, your discretization is now linked more towards that one. You can get high accuracy with only a few of these points, right? So one could imagine you could even optimize the number of points, and especially with something like ballistic motion, you know it's almost parabolic. So you probably only need like 3 or 4 points, to be entirely honest, right? And if you know that everything is actually changing, you know, when it's in the middle of the air, right? But when it actually hits the, when it actually gets like in the beginning, for example, when it's taking off, you know, those are kind of the important points. So you can cluster all your points around there. Spectral methods can achieve something called exponential convergence, which is the best, actually, or at least the best that we've been able to find, as opposed to quadratic convergence, right? So the Newton's method is good because it converges quadratically. Fourier analysis can actually converge exponentially, which is even better in terms of the number of operations that you need in order to solve your equation. Magic is the answer.
Wait, sorry. X to the n.
Yes.
Would that be like drastically worse than or sorry, n to the 2/3?
Well, yeah, but depends on the end.
Oh, okay.
Yeah. Okay. You could have higher, I think. Yeah. Dun, 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 dun. I'm not sure, actually. I'm not sure if they're talking about the root finder algorithm that converges exponentially, or they're talking about the discretization. I honestly don't know that one. I have a feeling they're probably talking about the discretization. That just by having the step size, you're increasing it exponentially instead of some like normal power law. Yeah. Okay. Drawbacks, probably a lot more complicated, especially compared like finite difference is super simple. It's even a linear relationship, like no problem with finite difference. Computational cost. I mean, yeah, kind of the same thing. We're stuck with solving linear large systems. And you do have to be careful with the stability, right? You do have to be kind of careful where you're putting those co-location points in the first place. Okay, let's try it. So this is our ballistic equation, the exact same, but now let's try doing with splines. So this is our function. This is still being broken down by that yeah. This is still being broken down according to the reduced order part. But now what we're doing is we're doing this method solve BVP, which is the NumPy version. All right, this is their tool. What you do is you basically do the exact same thing. You give it a set of values. You have it solve it, a set of points, your x values. You give it an initial guess for what y is, and then it's fitting a cubic spline, iterating. So it doesn't actually look very useful These are the succession of points that reaches that parabolic profile. You can kind of imagine seeing that this one starts here, jumps there, and then it jumps up actually very close. So if you actually output the values, then you would see something, but it's not so clear what how it's actually going. So I just don't think I think I nixed that line entirely. But it works, again, it works well, especially for 1D problems. For 2D problems, you need something like RBFs. Okay, so this is a big thing for using RBFs, and I think they use RBF networks too, which is somehow related to neural networks. Like that part's beyond me. Okay, so let's use RBFs to solve this nice equation, this Laplace equation, right, on a unit square with the boundary condition that everywhere is 0 afterwards. So what we have to do is we define the number of nodes, right? That's our discretization spacing. We define, if you remember, when we're doing RBFs, we're going to have to use a kernel. Let's use the Gaussian kernel, which requires this parameter epsilon. Epsilon should roughly be the distance between these points. That's the scaling of these RBFs. So that's what this guy's doing. The kernel is here. That's our Gaussian profile. Laplacian RBF. So here's where the magic comes. We know if we have the kernel, especially with a Gaussian, it's infinitely differentiable, right? It is, I forget what the terminology, I think it's compact or something. But like you can just keep taking the derivatives. So if you make a function which is sum of weights times exponentials, right? X and Y. You can always take this derivative. And you can take it down to like however many degrees you want it, however many derivatives you wanted. Okay? That's what this guy is doing. So what you do is you take this expression, you take the Laplace derivative, and you put that into your residual. That's what this function is doing. Then you define your mesh, right? That's in the X, the Y, you do your mesh grid, you ravel it so that it works right. You calculate your pointwise distance, which goes into your radius, apply your RBFs, and make your function. Right? You can go through this in your own time. You do have to identify, you do have to remember to apply your boundary points to put that into the matrix so that you know that at X is equal to wherever X is 1, that has to be 0. Wherever X is 0, that has to be 0. Same thing with the Y's. And then you solve. And what you're solving for is the weights. Okay? You want to find your solution, your actual solution, and you plot it, and lo and behold, you get something that looks reasonable, right? The question is, why would you do this instead of find a difference? I will show you. Despite my moratorium on live demos, here I go again. Instead of defining the points with some kind of regular grid, let's do a completely random sampling of points. We put that down here, and I think I have to nix this guy so that it works. And there we go. So this is a complete random sampling of points, and we actually still get a pretty good solution. I've seen it better though, so let's rerun it. Right now we've got a different set of uniform points, uniformly randomized points, and we still actually get a good solution to this, right? So you can imagine, right, like where would you want more points? Open question, guys. Where would you want more points?
Well, because I was thinking we wanted near the top, but then
Why?
then I was also thinking top doesn't have, like, I don't know, at least the other picture we saw, I kind of see Bill. So you don't want it on the sides. The sides are changed.
Let me put this back on because this actually solves it and shows you the surface well. So you're saying you would want it on the sides?
Because like the top seems
Okay.
so I'm like, I might want more points on the sides so that you can.
Okay, okay.
Well,
Anybody else? Thoughts? Okay. Laplace's equation, it's all about the curvature. It's all about the second derivative. Where is your second derivative? It's at the top. Because that's even though it's kind of flat, that's where all the second derivative is happening. On the sides, it's just kind of on the sides, it's actually the same because it's just basically flat. Right? Generally speaking, you want your points, your sampling, and this applies to finite element method too, when we can actually control this. You want your focus of points to be wherever things are changing. Where things are straight and lines, you don't have to worry about because you can always just do a linear interpolation for that. Any questions on collocation? Because of the way that it's plotting. That's why I had to turn it off. So the surface plotter is expecting uniform x, y, and u coordinates. And because the x and y do not correspond to the points that I'm giving it anymore, now it's just completely randomized where those values are. Yeah, I couldn't figure out how to get it to do a surface plotter that for a general surface. I'm sure it's a simple modification. I just didn't get to it. So, any other questions? Collocation? Okay. I put this back on because next year I'm going to be putting it in here instead of like 3 weeks ago. So just as a reminder with finite difference, we're going to be using finite difference to explore PDEs. That's why I want to show it here, because it's very clean and you can kind of conceptualize the time stepping method using finite difference pretty well and analyze the uncertainties with it. Do you guys remember the basic principles of finite difference? Very quickly, yeah. I mean, it was on your exam, so at this point, you guys should all know. But again, the whole point is that you take like the regular discretization and you say that one minus that one with some constants in between, give you the derivatives, blah, 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 blah. Off you go. Got very simple. You can get very high order estimates. Very.
Like I know in our like the matrix that that's actually like a very common.
Yeah, very, very common. Less common are the banded. But like finite element method will commonly give you sparse matrices. Necessarily, frankly. RBFs have a problem because they're dense. Technically, all points talk to each other, so you can truncate them, for example. But yeah, sparsity is your saving grace. Okay, finite difference. You can do depending on your geometries, you can do your approximations very efficiently because you use those balances to cancel out the errors. Works well with structured grid, higher order approximations, pretty limited flexibility. The accuracy can be limited by round off error and things like that. Then you have boundary conditions. So the problem with the boundary conditions here, and this is relevant to the finite volume method, which is next. If you remember when you get to a boundary and you have something like, if you have Dirichlet and you just say this function value is 10 over here, no problem, 10 is 10. If you say that the slope is 2, right? In order to say y prime is 2 in finite difference, you actually need to influence this point 2, right? And the problem is, this is the problem with the approximation, right? By doing this, you're saying that this point is also influenced by the boundary condition. So the effect of the boundary condition propagates farther into your sample. That's a bit of a weird way to be talking about it until I show you the alternative, which is finite volume and also finite element method. Okay, and with that, oh, go away.
Let's talk about it.
Yeah. But honestly, like the teams and everything, like sharing with the video and stuff is such an enabler. Okay. Finite volume method. Up until this point, what we've been talking about is finding points or a set of points or in some way where we can find the derivatives, right? Great. Instead, let's look at the integral of a function value around these points. So instead of looking at here, we're going to look at what's going on with our function in these boxes. Why would we ever want to do that? The integral of, I struggle with the order that I presented this stuff, and I'm still not quite sure I fully optimized it. I've converged on a solution. A lot of problems that we encounter in physics, and by a lot, I mean almost all of them, are conservation problems, right? Where you only have so much money, right? Money go in, money go out, however much is what's still in your bank account. Heat flux, I have an example. I'll go through the examples. The integral method you'll see is actually very, very conducive to that and helps and naturally satisfies that, which is very powerful. In particular, finite volume is encountered a lot whenever you have advection, right? Do you guys remember what advection is? Advection is, don't you hate when profs say advection is a term that looks like this? Advection is something like, so you're on the side of a stream, right? You drop in some dye and the stream isn't moving, stationary water, right? That dye is just going to disperse, right? That dispersion is due to molecular motion, Brownian motion, that is diffusion, right? Now you're in another stream and the stream is actually running. What you're going to see is your drop is going to start off here. It's going to disperse and disperse and disperse and disperse as it's going down the stream, right? That's two separate effects. That's diffusion, which does that, and advection, which is the movement of your material underneath. So fluid dynamics, as far as I'm aware, loves finite volume almost exclusively because fluid dynamics is all about advection. That's the biggest problem. That's the computational difficulty with computational fluid dynamics is that you're solving for velocity fields that are moving with velocity fields, and they're the same velocity field, right? And it's like it's this big complicated mess. What you're going to see is that integrates into something real simple. Okay. Contrast this with a finite difference method that solves these equations through approximating those derivatives, right? This is a different approach. What you do is you define a control volume around each of your nodes. You integrate inside it, and then you apply the divergence theorem, otherwise known as Green's theorem. There's this whole story that's like the three methods are actually two methods or something like that, right? The whole point is if you have divergence terms and you integrate over those divergence terms, that turns into a surface integral. Does that make intuitive sense to everybody? It's actually super simple when you think about it, right? Like divergence is all about spreading out. So all you do is you look at what goes through your boundary. Hooray. Okay. This is really nice because you get conservation equations all over the place. When advection is present, what you get is a lot of very sharp gradients because you have material moving. If this material is moving faster over here and this one hasn't kept up, then you're that's say you have a concentration field that looks like that in the street, right? You're moving this way. You're in a stream, right? So you normally have non-slip on the boundaries, and you're completely free to flow in the center of it, right? This part is going to be stretched. So you can imagine the progression of this diffusion and advection is going to be going like this, like this, like this, like this, right? And it's going to get super, super concentrated, right? Consider the gradient here. That gradient is going to be massive. Super, super high gradient. If you were throwing finite difference at it, you would have to resolve that mass, which means that you need super fine discretization everywhere. Giant pain. To the point where when people do advective problems with finite difference, they introduce something called artificial diffusion, which is literally a diffusive term to help break down those super high gradients. That's how they achieve numerical stability. Finite volume doesn't need that. So very quickly, because I'm running low on time here, some examples of conservations are conservation of energy, of conservation of mass, right? Literally the rate of change of mass in a volume, rho, density, mass in a volume, is proportional to the divergence of that mass going through the volume. Hooray! Same thing with conservation of momentum. There's like 150 ways to write Navier-Stokes. This is one of them. Basically, what this is saying is that the conservation, right, your balance here depends on your viscous diffusion, right? Viscous stress, which is this amount of water moving with respect to this one and kind of dragging on each other. And then you also have the fact that this is also moving, actually, in a moving frame of reference. That's what this describes, but you're still in a divergence term. Conservation of energy, the same thing. Now you have energy that's moving along with your stream and your heat transport, heat conduction, electric charge, dilute species. So that's this example with the material moving down the stream. All of these are divergence terms. So if you integrate over these guys, this becomes a surface integral through your boundary. It handles flexible meshes. It handles irregular meshes much better. And this is an example for how it does it. Basically because it better separates out the effect of different boundaries. So this is an example out of the textbook from last year that was looking at this material, which is insulated on, so it's two materials, it's two metals put together, right? Blue and gray. You're insulated on one part. You have convective heat transport on another side, and they're also different materials, therefore different thermal conductivities, right? And what we want to know is we want to know the temperature distribution around this particular node, or two. What you do is you consider, okay, we're doing steady state heat transport, right? There's our heat flux. This should be a lambda in here. Dun, 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 dun. Yeah, let's define our control volume. There are different ways of defining our control volume depending on the type of element you have. Finite volume, usually they'll even use like more exotic cells, like hex cells and stuff like that. The way that you can define these ones is just by doing the midpoint of the line. So this is the line here, take the midpoint, draw the line down. Here's your line here, draw the line down, but this one, because it has a different mesh spacing, you define it a little bit differently, but now here's your box. All you have to do then is sum your fluxes through the boundaries times the area of those boundaries, right? So here's J on the left. How much area do you have? You have H over 2 times whatever your thickness is, right? J on the right, same area. Lower here, there are actually two heat fluxes on the bottom, right? Finite volume doesn't care. You can do the lower in the material A, which is this one, going up times H over 2. This flux is only H over 4. It doesn't matter. All you have to do is just sum these guys, and then you have convective loss only on this part here. Then there is one caveat. You do still have to do a bit of finite difference, but generally what you do is forward and backward. You don't even do central finite difference, and that's because you might have an irregular mesh, so there's no value to it. So you do the finite difference on these different nodes. You put that in, and I thought I had a breakdown. I guess not. Once you simplify it, you get an algebraic system of knowns. These are all known quantities. You have a vector of unknowns, right? You solve it using LU decomposition, linear systems, right? Woohoo! This should bring flashbacks of finite difference. Like this looks like finite difference at this point, right? For the case of regular grids, it exactly decomposes to finite difference. But once you get the irregular grids, you know, finite difference doesn't really handle them efficiently. So this is a great way to do it. When we get into the PDE versions of this, I'm going to try and talk about the, what's this thing called? There's a stability criteria for handling advective terms. finite volume, because of that integral representation, has better behavior for those vector terms. Finite element method, there is a class of finite elements called discrete finite element methods that have like kind of similar properties. I don't think we're going to get there. It's a bit advanced for this. Okay. They're a lot more flexible. They handle the conservation inherently, which is a really big part of it. Unstructured methods, boundary conditions work real well, especially when you have like even differing boundary conditions. Heat flux depending on your position, no problem. And it's very robust. They are more complex. They don't have as nice structure to them, partly because of the unstructured grid. Okay, computational cost is the same with everything. You also lose out on that nice property of like central differences and things like that. So you are a little bit handcuffed by the order accuracy of that. There are numerical diffusion techniques, which are ways that you can kind of handle the sharper gradients, but it's still stable for it. And the CFL condition is that instability there. Any questions?
Once I get experience.
Okay, it's 6:10. I've got like 10 minutes here. Let's talk about partial differential equations. So PDEs are basically expanded ODEs to include multiple dimensions. Other spatial coordinates, X, Y, Z, are basically just an extension of the boundary value problems. That's how you're going to treat it. The problem is time. Time has to be an initial value problem because you generally don't have the end of time, the value at the end of time. In some cases you do, actually, but generally speaking, you don't, right? And that kind of mix up is where you get the problems. Yeah. Introduction of time raises the question of how information is propagated in your system. This is the basis for the differentiation between elliptic, parabolic, and hyperbolic equations. Have you guys spoken about this classification in other classes, like differential equations, I guess? Yeah. How far did they talk about like characteristics, for example? Okay, so I tried getting this information into here, and I quickly realized that it was way too advanced for me to understand, let alone present. And to be frank, it's nothing to do with numerical methods because there's only one method that I'm aware of that actually uses those characteristics. But don't worry about it. It's all about how information propagates in your system. So elliptic equations are ones that don't have time. That don't have time as a differential form. Right? So what that means is that you have only spatial dependence. It means that the information is not being propagated. In other words, all of your propagations, all of your ripples in your pond have dissipated and you are now at a steady state. It does not mean that your solution is not time dependent. You could have quasi-static cases, right? Elasticity is typically modeled as being quasi-static because otherwise it's the speed of sound, right? And nobody wants to deal with the speed of sound because then you would have to time step on the rate of 1/300 meters a second, right? So what you do instead is you have these parameters that are time dependent. And then at every time step, you solve it as if all of your dissipation has already happened. Examples include steady state or quasi-static equations, right? Laplace and Poisson's equation. I don't quite understand why Laplace's equation isn't a subset of Poisson's equation, but whatever. Electrostatics is a big one. Heat transport is another big one. Fluid flow in the absence of a sink or a source of fluid can be modeled under certain cases as, and I forget what those cases are. You can model the velocity potential instead of the velocity itself. That becomes one of these types of equations. And then the difference is, do you have a charge for electric potential? Do you have a heat source, right? All of my assignments seem to have a heat source, right? Because I'm a nuclear guy. That's what happens. Okay. Helmholtz equation. This one might be a bit surprising. Helmholtz equations are of this form. You have the spatial and a function of your actual variable. The funny thing is that those equations include acoustics, which are waves, and quantum mechanics, where you're looking at the wave function, right? Does anybody know why this is considered, why we're talking about wave behavior in the context of elliptic equations? Buddy? right? If you remember, do you remember talking about separation of variables? As a general technique, do you guys remember this? Yeah, okay. So what you do is you say that your function is a product of one function, one time-dependent part that only depends on time, and another spatial part that only depends on space. You separate them out, you say that that's equal to a constant, in this case, k squared, and then you solve them individually. Turns out that those k squareds are actually your eigenvalues for these things. And what you've done is you've separated out, we'll probably circle back to this next week, 2 weeks time, when we talk about eigenfunctions. What you've done is you've separated out your spatial dependence and your time dependence. And just as I was being the dork that I am, I got a coffee earlier and I was staring at my cup. You know how when you're walking, you can see like the waves and stuff like that? Those waves never change, right? It's always the T-Rex pattern, because I grew up with Jurassic Park. Thing stomps and you see the nice little bell thing. Have you guys watched have you heard of the movie Jurassic Park? Okay.
We watched it.
Yeah. Not the cartoon, not the like the original. Ah, excellent. On VHS?
Okay.
Beta. Right. So again, right, because you have that spatial function, which is your eigenfunction, but it exists and then it kind of tapers off as the time-dependent term goes in, acts and dissipates that, right? That falls into that spatial part is of the form of Helmholtz, which is kind of nice. Okay, solution approaches. Elliptic equations generally amount to solving the system of nonlinear equations simultaneously, right? We saw that with the boundary value problems because you know what's happening here. You know what's happening here. You just find some kind of consistent solution at every point inside your function, right? Remember, though, that now so when we were talking about this originally, we were talking about like root finding in 1 dimension, 2 dimensions. Now we're talking about root finding in 1,000,000 dimensions, right? Because now we're discretizing our spatial domain and every single point to that is an unknown function. So all of the pitfalls that we first discovered with root finding now apply in spades, right? So a big problem is a good initial guess. Okay? This can be actually a massive problem when you're doing this sort of stuff. An example of an elliptic problem that's terribly hard to solve is natural convection, if you believe it. Super simple, basic phenomenon. Almost all solvers will immediately die. And the problem is that what happens is that your Newton solver root finder isn't able to converge on a solution. So you need to do damp Newton steps. You have to use trust region, blah, 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 right? What you have to do is you parameterize some part, which is kind of introducing almost a time stepper. So for example, you take your pot of water is the quintessential example, and you gradually turn on the heat. So at 0 heat, you have stationary. You can solve stationary. Good, right? You turn it on a little bit. Now there's a little bit of velocity, but that little bit of velocity is close enough to your previous one. And hopefully, you can progress in a way that actually works, right? I think there is a term for this, something about like topology, isomorphism or something. I don't know. But the whole idea is that you arrive at your initial value, like the final solution for every step becomes your initial value for the next. And you slowly bring it up and up and up until you get to that steady state. But then you get all kinds of weird phenomenon kicking in, right? Like natural convection is actually kind of complicated. The other problem is convergence, especially with high dimensional problems. This is where your root finder, which is basically looking for the answer, right? Well, now you have a mountain that has 1,000 dimensions or 1,000,000 dimensions that you can choose. It can get wacky. There is a subtle issue which has really emerged when you talk about parallelization on different computers, on multiple computer systems. So all of the modern HPCs, you don't have a single powerful computer. You have 1,000,000 actually kind of basic computers, basically like cell phone quad CPU cores. The problem is, so this is where like preconditioners come in. Remember those, right? This is where preconditioners come in because they provide a way to separate out these problems. So one common way to do that is domain decomposition. I think I did talk about this a little bit. What you end up doing, I've got you next slide. What you end up doing is you take your spatial domain and you chop it up, you partition it, right? This part goes over there, this part goes over there, this part goes over there, this part goes over there. When you have elliptic systems, the information propagates instantaneously from here over to there, right? But it can't do that because this chunk doesn't talk to that chunk. This chunk talks to this chunk, talks to this chunk, talks to this chunk, talks to this one, this one, this one. Finally, it gets over there. Now that has rebounded. And it goes da 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 da, right? If you have a large system, it's going to take forever. And this kind of sinks domain decomposition. It still works, but you end up having to have more and more and more iterations. And what that is that information pulse that's synchronizing and moving between these things. There are other methods. They're called multi-grid methods. If anybody still wants to do a research project and wants to see kind of a cool one, take a look at multi-grid methods. Essentially, what you end up doing is you take your domain and you discretize it with different size meshes. And you solve it. So you solve it with a big mesh that has like 10 elements, right? 10 intervals. Then you subdivide those intervals and you say, okay, now I have 100 because each one became 10. And you can do that again and again and again. It ends up, the error analysis ends up working out in terms of Fourier space. So what you do is you reduce the error on different wavelengths, right? Your coarse grid is small enough that this one actually does communicate with this. You can solve it as a direct problem. But then you can go down a level, remesh, resolve your problem, go down again, solve it on a finer interval, down again. And that's a way to divide it up and bring it back in an efficient way. And multi-grid solvers are probably the best right now that we know of to be able to solve these things. I think I'm out of time. So I'll pick it up tomorrow. It's a long lecture, I apologize. I think I talked more about living in Deep River than I did about PDEs. Let's start, guys, because we've actually got a fair bit to talk about today, and everybody wants to get out on Thursday night. Okay, so we've got to get through the rest of the partial differential equation lecture. We wanted to go over assignment 6. And then I'm going to show you assignment 7. It's almost done. I haven't released it yet because I need to assign the marking and stuff like that, but we can at least present it to you guys. Okay, where did we end off yesterday? Is it solution approaches? I remember talking about that guy. Yeah. Did we talk about parabolic equations? How to solve them? I don't think so. Okay, so parabolic equations. Any equation of the form something di by dt minus something else that's at least squared. So something like this kind of the quintessential heat transport equation, right? You've got the second derivative of space, you've got the first derivative of time. It's called parabolic. All of these names have to do with the way the, let's see. In a nutshell, it is the way that information is propagated, but it's more complicated than that. It's something called the method of characteristics. And the parabolic ones basically go up. Hyperbolic go up and down, which means that you can rotate it around as a conic section, and that's a hyperbolic function. These are all parabolic, therefore they're only in one direction. That's where all this stuff is coming from. Elliptic, I'm probably following that, right? If you think about a conic section, you can either have an ellipse where you're sectioning it like that, a parabola where you've got it to the side, or a hyperbolic thing where you see both sides. So that's probably where it comes from, but I couldn't wrap my head around the theory to be able to distill it down, to be entirely honest. Okay. Funny thing about parabolic equations is that they only propagate information in one direction. That one direction happens to be forward in time. So parabolic equations tend to be diffusive processes, heat transport, mass transport, anything like that, anything that smooths out discontinuities. So you can imagine that if you have a spike of a dye or a species in a bottle of water, it spreads out and it kind of diffuses. What that means is, yeah. Okay, so It is nice because it tends to damp out small oscillations and discontinuities that you might have started with, but it still doesn't guarantee convergence, unfortunately, and we still have stiffness emerging from this stuff. Let's see. This actually still violates causality because what it ends up meaning is that you have an infinite rate. So elliptic methods we spoke about has infinite rates of propagation of information. One part knows about the other part instantaneously. There is no time dependence. Parabolic still has that feature, but now it's a little bit more subtle. If you think about the heat balance equation and a heat flux, in this context, the heat flux is instantly aware and can instantly respond to any kind of disturbance in the force, actually. You guys at least get that reference, right? Disturbance in the force. Okay. Yes. Let's see. Not actually important that the infinite rate of propagation. All this is to be contrasted with wave equation, which are basically acceleration, right? So acceleration is actually the world that we live in. This is actually technically an approximation of it. Okay. Solution schemes. Generally, what we're going to do to solve parabolic equations, something called time marching. What that means is that we're going to discretize time as an initial value problem and space as a boundary value problem. And depending on our time stepping scheme, we're going to see we get stability, implicit versus explicit. We haven't escaped any of this stuff. It's a very common thing to want to solve something called the inverse problem. What that means is that you want to take your result of your simulation and back calculate some property of the equation itself. So kind of a common one is if you do an experiment where you're heating something on one side, you're watching the temperature on the other side, and depending on how that temperature varies, you're going to want to find out what the thermal conductivity is, right? So you're trying to use that signal to back calculate some property. It is nefarious. It's next to impossible. The best you can do is like kind of a statistical treatment. In very, very certain circumstances and well-controlled circumstances, you can get a pretty good estimate. It's called the laser flash method. But it's hard. This is a property of the fact that the information is only propagating in one dimension, in one direction, and that direction is forward in time, not backwards in time. So that information tends to get blurred out. If you consider like getting a blurry photo, despite what CSI tells you, you can't unblur a photo. I mean, you can, but it's like you're not actually going to see all the additional detail kind of coming out. Yeah. There are some interesting applications with AI for that. For situations where you don't actually care so much what the unblurred photo looks like, you can de-blur it. And that's apparently useful for video games.
Yeah, but you're just like.
Exactly. So for situations where you don't actually care whether or not you're right, it works great. Hence like NVIDIA. But, oh yeah. Hyperbolic equations are the wave equations. They have the second order time, second order space. This is literally driving, right? Since somebody pointed out to me long ago that like when you stop at a traffic light, have you ever noticed how like traffic goes in waves? Right? Like you start at the traffic, it kind of has that long kind of wavelength. You can see the cars going ahead of you, they stop. Finally, you can go through the light, but now you have to kind of stop again. The traffic in the middle of like the highway, and all of a sudden you're slowing down for no reason whatsoever. That's also because of the wave phenomenon. Like I mean, it is actual physical reality, right? The funny thing about waves is that they propagate time both forward and backwards equally. So if you did have some kind of wave behavior, you could actually propagate it backwards in time. It's something called time reversal invariant. So literally you could take t, replace it by minus t, and you go back in time. What's nice about that one is that you can reconstruct things before you measure it, actually with a measure of accuracy, which is kind of neat. So an example of that one might be, let's see, not really triangulation. If you saw like waves from a small tsunami or something, so you don't want to see waves from a big tsunami, right? And you saw it in different places, you could back calculate where that came from. right? And that's because those waves didn't diffuse necessarily. There is some scattering, there is some dispersion of the waves, but it's predominantly reversal. And therefore you can calculate where the fault was. Okay, solving these guys. General approach, again, is to discretize time and then discretize space. And then it's a question of whether or not you're discretizing space based on your current time step or your previous time step, explicit, implicit, right? And then you just step forward. There's a W in forward. Ba, 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 ba. And you update your boundary value problem accordingly. Let's look at the parabolic case, since we can usually change the second order time derivative through reduction of order into a coupled set of first order time derivatives. Do you guys remember how to do that? If not, look back in the notes. Check out the reduction of order. It's a nice trick, and it's actually kind of like the de facto way that you're going to be modeling this sort of stuff if you're doing like finite difference or finite element. Okay, so this is nothing new. This is just the finite different expansion of the second derivative. Alpha is our thermal diffusivity. A little bit of notation here, because we're going to be doubling up in both space and time. At least I'm going to try and stick to 1D, at least, but right. But you can imagine what happens when you get to multidimensional. The spatial index is going to be noted with a subscript, an index with an I. So Ti, right? Ti -1, Ti +1. Temporal index is going to be a superscript, and it's going to be indexed by T. So at least try and be a little bit simple. I'm going to try and keep the known time step as T, right? As just the T index here. And we're always going to try and calculate T +1. Okay, so I'm going to try and keep that notation just to help it keep it clear. Okay. As we talked about in the initial value section, the explicit Euler scheme is just calculating the next time step based on the current one, right? So that is TT +1 minus TT over whatever your temporal step is. When you put that into the PDE, you get something that looks like this. So again, we know temperature at TT. I didn't think about that one. We know TT. What we want to find is T +1. Okay. And the explicit Euler is saying T +1 is an explicit expression of our known quantity, TT. Does that make sense? Okay. I am simplifying a little bit. I just defined this constant R here to be this ratio of the step sizes, and I'm throwing alpha in there too. It's common to kind of show these things using something called a stencil. This is the stencil for the forward Euler time stepping algorithm, which is the explicit. I should put that up there. Basically, what we want to do is for temperature at this position, right? The next time step depends on the previous ones. So the previous one and one on either side, it's central difference for a second order. The nice thing about this is that the next time temperature in our future step only depends on the current one. It doesn't depend on anything else. So we can run our little model here. Here's the magic here, T new, so they have a better naming scheme than I do, right, is equal to the previous one plus alpha, change in time, change in space squared, times our ones on either side. And we take a step forward. Yes, pretty sure it's okay. Running. Okay. This is a slider that's changing the time step. So we're fixing our spatial discretization. I'm just changing the time step. That's the delta T. And we can see the result. These results are, I got a bit lazy, to be honest. I plotted, I think, 10 time steps, but I didn't normalize it to the time. So as we increase time steps, you're going to see a bit of a change because it's taking longer time steps, right? So it's going a bit into the future, okay? Ignoring that though, right? Kind of like we saw with the initial value problems, no problem. Everything's fine, everything's great. And all of a sudden, everything goes to shit. Right? Do you have any idea why this is happening? Was that almost? Kind of, but this isn't polynomials. Anybody? Yep. It does indeed. Same thing as we saw with the implicit. Like remember the explicit time stepper that all of a sudden for seemingly no reason just died, right? This is the exact same phenomenon, but now it's the proper way to look at that. In the previous step, what we did was said, yeah. Yeah, the previous one wasn't such a good treatment. It was a nice like toy example, but this is the real thing. Okay. It's a bit more complicated. Yeah. It depends on alpha. Yeah. um, if you think about it, right? Like all this has to do with transmitting information and propagating information. That's why the time step, the ratio of the time step to the space step is the important part. And then the material property involved with that is the thermal diffusivity, right? So it's your kinetics of the physics and then your discretization. And all of it together has to be stable so that you avoid this. Okay. The difficulty here is that now we have to consider, like before we were just kind of like taking one point and stepping forward in time, right? And we kind of made a nice little analysis that yes, it does actually decay, blah, 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 blah. Now we have to consider a whole bunch of points. Now we have to consider 10 points and how the future step of those 10 points is going to be stable or unstable. And the way that we do that is through something called von Neumann stability analysis. Ever heard of it? Not surprised. It's a really cool analysis technique. Like what's nice about this is that we start to get into the actual understanding of what's happening in these equations. Yeah, let's look at how it works. What we're going to do is we're going to express the solution as a Fourier series, and we're going to see whether or not the high frequency oscillations grow or shrink. So the idea is that because it's a numerical method, we have finite precision, we have round off error, we have truncation error, right? And on top of that, we also have our time integration scheme, which is introducing yet more error, right? So you can imagine you're generating all this noise in your signal. When you take the next step, does that noise, which is high frequency oscillations, decay or does it grow? Because if it grows, you're sunk. Okay? So let's define yet another subscript, this time because we have a nuclear slant, I'm putting it on the left-hand side, which has caused some of you guys to go into convulsions. What we're going to do is we're going to look at the kth wave of the solution. So at least we don't need to do like the full Fourier spectrum. We can just look at wave k. Okay, it is defined as exponential j because now we have index I, so j has to be the imaginary number. This won't be on the test, guys. I'm not going to test you guys on von Neumann stability analysis, so if I gloss over things, don't worry about it. Or if the blast shield comes down, like don't worry about it. I'll try and highlight the key points, right? What you're going to do is you're going to look at the kth wave. Can be expressed as an exponential because complex analysis, right? And what we're going to do is we're going to compare what happens to that wave at time plus 1, our future time, versus compared to our current one. We define our growth factor, which is literally the multiplication of that wave from one step to another, and we see if it grows or it doesn't. Because if it is less than or equal to 1, then it's not going to grow. Ideally, it's going to be less than 1 because that means it actively shrinks. But failing shrinking, we at least don't want it to grow. Yeah. When we put this equation into our explicit time stepper method up here, because of the nice properties of exponentials, excuse me, some of these coefficients come down, we multiply them through, we collect like terms, and we actually recover our initial t at time t, the wave, the kth wave of that. Divide those two out, we get a growth factor, and I think it's Euler's expression that gives us the cosine here. Okay? Because it's a cosine, we know, right, what are the limits of cosine? What does cosine go to? Yeah, right? So we know that it's only going to go between negative and 1 and 1. So we don't even need to calculate what delta x is right now. We just need to say that this is either going to be a 0, in which case we're going to have a 1 out here, or it's going to be negative 1. Oh, sorry. Let's see. If cos x, if the cos is negative 1, then we're going to get this guy here, this expression. If it's positive 1, 1 minus 1 cancels out, and we just get the 1 remaining here, right? So this is setting our limits. Because we can set our limits, we can say that in order for g to be less than or equal to 1, this has to be true. And this becomes our stability criteria. If you forget everything else from this lecture, remember that there is an explicit form for the stability of explicit time steppers. I can't say that it's going to be on the assignment, but it'll almost definitely be on the exam. So excuse me. Intuitively and nicely mathematically, if we were looking in higher dimensions, this would just add. Right? So what we would be looking for is the kth wave in both x and y, and our stability criteria is just adding onto it, right? Assuming that we are in a rectangular grid with step size h. That's why there's h here instead of delta x. Similarly for 3D, it's just 6. Okay, so at least there's some kind of nice properties there. Once again, what this means is that we've come up against a stiffness issue where our time step is limited by numerical stability instead of accuracy, right? And this is the problem, but it's actually a pretty nice expression, right? It's not like kind of a nebulous, oh, that thing is stiff. Like, no, it's stiff, but it's according to this, right? But we'll come back to that in the summary. The alternative to forward Euler is backward Euler, otherwise known as implicit Euler time stepping. It actually looks exactly the same, right? Except this time when we write out and we do the spatial discretization, now we're going to do it at our future time step. Okay, so now we've got t plus 1, that's our previous time, and we've got this mumbo jumbo, these are all at the next time step. So when we look at our stencil, it's inverted, right? Our current one is consistent with itself, and it just depends on the previous one time, not on both sides. That's the next one. If you look at the error analysis, it's super easy. Like all we've done is flipped the t plus 1 and the t. So what that means is now 1 over g is in the same range. And that is always true, regardless of your parameters. Assuming that alpha is positive, alpha is always positive because that means that you are propagating forward in time. If you had alpha negative, then you would be going backwards in time. Yeah. It would mean like thermal conductivity would be negative. Thermal conductivity, your density, and your heat capacity would be some combination of negatives. Like that. It's never the case. It's impossible. The problem with this, anybody see the problem? It's the exact same problem as with normal implicit Euler, right? But now it's the problem on crack. Absolutely. Because now you have to solve for for all of your equations, all of your variables simultaneously, right? And that's the problem. That's the sinker. But when we run it, right, doesn't matter what you do, it'll always converge, which is nice. Any questions on those two? Okay. Pop quiz. What do we do when we have one thing going one way and another thing going the other way? We've done this like 3 or 4 times now. You always want the center, right? You have forward difference, you have backward difference. Hey, you just average those two and you're going to get a higher accuracy magically, right? It's not actually magic. It's because the error of one cancels out with partially the error of the other one, right? It's like, honestly, the next time, like next year when I'm teaching this, I'm just going to put out in front like 3 or 4 like key points. Here's what we're going to be doing. We're going to be doing Taylor series at the wazoo. We're going to be canceling the forward and backward error. And there was something else that I picked up on it. I can't remember now. Okay, Craig Nicholson. The problem with the backward Euler, it's very robust, but it's only first order accurate. Meanwhile, central difference for the spatial discretization is what order accuracy? You've already answered 2 questions. Are you? Peanut gallery on the right? Nobody? Okay, well, if it's not 1, chances are it's, there you go. Pretty safe assumption, right? This description is not so accurate because generally speaking, your time step will not be the same as your space step, right? But it would be nice if you could at least achieve the same order of convergence. Not order of magnitude, it's the same order of convergence between those two. Fortunately, you can. You average them. Again, you start off with the exact same temporal description, but now when you discretize space, you do the average of the future time step and the previous time step. And when you put it into Mathematica and you tell it to simplify, what you get is this expression. It goes pissing them off. It looks ugly, but it turns out that it's the exact same matrix structure. Because again, all you've got is T to the left, T in the middle, T to the right, and some combination of things behind it. The stencil now looks complete because we've literally got both on either side. And when we run it, this is now the time index instead of the step size, skipping to the good stuff. Not surprisingly, backward tends to overpredict because it's taking the future value. Forward tends to underpredict because it's taking the previous value, and you average the two and you get almost exactly in the middle, right? As you would expect. But this turns out to be second order of time. Second order in time step, which is nice. Okay. Once again, we've seen the value of implicit time steppers for solving stiff equations, but they require a root finder, right? In order to solve the system of nonlinear equations. Those tend to rely on linear solvers. Linear solvers, right? What's the default linear solver that everybody wants to use? LU, right? What does LU scale like? If I discretize my space into 100 elements, right? N is equal to 100. How long would a dense LU take, roughly? No, N cubed. You got it. Accidentally, you got it. Right? So what this means is, and that's just one dimension, right? If you want to take, right, here's where our ends get a little bit muddled, right? If you want to discretize space into 100 elements, that's 100, your LU solver basically goes to 1,000,000, right? Let's say like 1,000,000, some factor of 1,000,000. Now let's do a 2-dimensional domain. Now I've got 100 by 100, so we're up to 10,000. 10,000 is what, 4 zeros, N cubed means what's 10 to the 12 trillion? Right? Now we go to 3 dimensions, right? And now we're 100 by 100 by 100 cubed. What are we up to, like octillion or something, right? The saving grace here is sparse, exactly. And if we, I forgot to uncomment this, but okay. Yeah, you see it's a sparse matrix, right? It's a sparse matrix. It's actually a banded matrix in one dimension. Sorry, in one dimension, it is a tridiagonal matrix. In more dimensions, it turns out to be a banded matrix because you have that constant factor of something over there, something over there. So at least you do get the nice structure. Sparse matrices tend to solve better than n cubed, but still pretty terribly. So if that's the case, typically you have to resort to iterative solvers. And here's the conundrum. If you're solving, right? So before I get there, explicit time steppers are conditionally stable. But as long as you are within that condition, and remember that you can calculate that condition beforehand, you know what that limit is. And as long as you're in that limit, you will converge to the right solution, right? The problem is that that limit tends to be pretty small. And even when nothing else is happening, you remember when we talked about the stiffness, and what we found is even when the physics is no longer depending on that stiff equation, it's still going to be there and haunt you, right? So even when nothing is happening in your model anymore, you're still going to have that stiffness that's not going to allow you to take a larger time step. And that sucks because you've reached a steady state and you just can't get there. Other benefits is that it avoids the pitfalls of a root finder. So there's no question of initial guesses, right? You don't even have to worry about that because it just calculates the next time step. It always converges and it parallelizes well because you're just looking at the previous time step. So you solve a part and you solve a part and you solve a part and you solve a part, right? As opposed to the root finder where you all solve a part, but everybody has to constantly be talking to each other because every part depends on every other part. So explicit methods parallelize very well, much smaller memory usage, and they don't need an iterative linear solver, right? So the question is, at what point does the additional cost of root finding, which is probably through an iteration, so consider two paths, right? You start from your initial value. You could take a teeny tiny time step and go to your next desired time. But you would have to do it really small, but hey, at least each one is really fast, right? And you can get everybody working on it together. Or you can take one massive time step. You could even take the entire thing. If you didn't worry about accuracy, you just jumped straight to the end, right? You could do that, but then to find the solution, you would need an iterative solver that choose and choose and choose and choose and choose and choose and choose around at it. At what point do those iterations exceed taking those small time steps? The answer is problem dependent. General multiphysics solvers, where you just want to solve physics, tend to be implicit because that's the most robust. And typically you would use LU within your root finder because that's also going to give you the most robust answer. Special software that's particularly designed for certain types of physics tend to actually be explicit. So some examples for that is almost all things CFD will typically work with explicit solvers because it's so wacky and so confusing and there's so many different scales of things happening there that honestly you may as well just do an explicit time stepper and farm it out to a bunch of different nodes. Another interesting one is something called LS-DYNA that I think was bought out by Abacus. I think it started differently. That's all the crash test simulations. So anything where like you have the car, if you look on the website, it's literally a car that's smashing into something, right? And you have all the bits, the glass is broken, something is impacted something else, right? Every single part of that is not only flying through the air, but like you also have like the vibrations and things and impact and crumpling and all that fun stuff. An explicit solver at it because it will converge. You don't have to do anything like contact. Contact is a nightmare because you have nothing and then you have something. Explicit solvers will work. So that's my summary of that one. Any questions on solving PDEs? Okay. These stability criteria for the explicit methods, we derive them in terms of the finite difference method. It is not only dependent on the finite difference. We're gonna be using the exact same time stepper algorithm for the finite element method, and it works exactly the same. It's the exact same condition. It's a property of, and probably the correct formulation, like I did in terms of finite difference, the correct formulation is probably like actual derivatives, right? And then when you do that, what you're gonna find is basically the same thing. Okay. No questions? No questions?